a Master of Science in Particle Astrophysics. And he's a research assistant with the Department of Physics. Over the last few years, he's been working on building one of the world's largest direct detection dark matter experiments in North America's deepest underground science laboratory, which is Snow Lab, near Sudbury, Ontario. He's also spent lots of time in national physics laboratories like Triumph and Fermilab, learning about and working on particle detectors. Please join me in welcoming Rhys Chouinard.
Now you know what I'm talking about and what my name is, so happy May the 4th to be with you and get right into it. So the first thing most people ask me is, well, Rhys, you're working on dark matter. I don't know what that is, but why do you even care about it? Okay, that's a valid question. So the short answer is because 27% of our universe is made up of it. So when astronomers look into the night sky with their really sweet telescope and they start adding up the energy density of the universe, they end up breaking it down into three pieces. So the stuff we know about, the stuff we understand, that's this little slice over here. That's 5% of the total matter is what we actually understand. These are things like stars, planets, gas, dust, humans, turtles, rocks, all of the stuff we're familiar with. That's this little sliver of the total universe. The next slice of the universe, coming in at 27%, is dark matter. That's what I'll be talking about. And then this really huge, embarrassing slice, that's even more mysterious than dark matter. And I'm not even going to go into it because we know even less about it than we do about dark matter. So this pie chart is a little bit updated from Ross's talk because there was a really recent result came out from a Planck satellite. And the short of it is we understand a small chunk of our universe, and I'm going to be talking about this chunk, which we're getting to know a little better. So what makes it dark? What does it mean for something to be dark? So to explain that, I have to go into some physics, and so we'll start by talking about the four fundamental forces. So all of the interactions that happen on Earth are governed by one of these four forces in some way. So the first one we'll talk about is the strong forces. This isn't as known about in everyday life, but when nuclear bombs go off, they're releasing energy, binding energy, and that's due to the strong force. So they're the reason things can go boom. The second force is the weak force. So this is how smoke alarms work. This is the force that governs radioactive decay. So the next force, the electromagnetic force, okay, most people can understand this one. This is what gives you frizzy hair when you rub a balloon on your head. This is also the reason your fridge magnets works, although Ross Lockwood doesn't know why. The last force, gravity. So this one's good because, you can look out and see the sun, and you say, that sun isn't getting smaller, which means something's holding me in place close to it. The reason you're held in place is because of gravity. So you can make the obvious note that physicists are really creative when it comes to naming these forces. So back to what makes dark matter dark. Well, dark matter has only been shown to interact with the force of gravity so far. That's how we've detected it. And people have hypothesized that it can interact with the weak force weakly, and that'll be important later after talking about how we might be able to detect it. And the real reason it's dark is because it doesn't interact electromagnetically, which means it doesn't directly give off light when we look out at it in the universe. So if my slide ever moves to the next page here, we'll get on. Okay, if it's dark, how do you know it's there, smart aleck? Well, the same reason you know air is there, even though you can't see it. You can look for the effects of air on things you can see. So if you start blowing into a balloon, the balloon takes form. Why? Because air is in there, and now it's exerting a force on something you can see. So you can say, well, I must have been putting something in there. Or on a nice windy summer day, like we rarely get in Edmonton, you can see the wind blowing through someone's hair or blowing through the grass. And you can say, okay, there's got to be something there because grass doesn't normally just wave back and forth by itself. So let's start with what we can see, the things we do know about. So every now and then I'll slip back into my physicist habit and I'll start to talk about baryonic matter. So just remember, baryonic matter is normal matter. This is, like I said, the stars and gas and planets, things that humans are made up of. If you don't know what a star is, it's a lot of gas that's fallen together on itself and started to fuse and give off light. If you have a lot of stars, like our sun, then you get something called a galaxy. And an important point for later on is that stars typically rotate around the center of the galaxy they're in. If you have a whole bunch of these galaxies together in a gravitationally bound area, it's called a cluster. So every now and then you'll hear me throw out that term. It's just a whole bunch of galaxies hanging out together. So this is the visible matter we can see. So I was telling you that dark matter influences the things we can see. And some of the very first really, really good evidence for dark matter came from something called rotation curves. So I'm going to go through this, and then I'm going to show an animation. So if you get confused, don't worry, I'll try and show it a little bit better later on. So a rotation curve, when you look out at a galaxy, you can actually measure how fast all of the stars are moving as they go around the center of the galaxy. And if you measure the speeds of these stars and then plotted their speed on the y-axis versus how far away they are from the center of the galaxy on the x-axis, you get what's called a rotation curve. And you can use some really simple physics to add up the matter, all of the stars and gas you see, and say, okay, based on how much matter there is there, what do I expect? How fast should the stars be moving at the inner parts of the galaxies and the outer parts of the galaxies? And so the rotation curve you expect is this bottom one. Just based on the visible matter you see, the stars should be moving really fast towards the center of the galaxy, and then they should sort of taper off towards the outskirts of the galaxies if all that's there is the matter that you can see. This is the same way that the planets at the outer parts of our solar system rotate a bit slower, and the ones that are closer to the sun move a bit quicker. So they expected this curve, right? They drew up all these really powerful space telescopes and looked really far at the galaxies. And all of a sudden, they got, again, this really embarrassing curve that did not meet predictions at all. And the stars are actually moving really, really quickly at the outer edges of the galaxy. And if all that's there is the visible matter, this makes no sense. These stars should just be flung out. They shouldn't actually be bound to that galaxy, but they are. And so one of the ways you can explain this is you assume that there's some spherical halo of dark matter, which is concentric with the visible matter, and that extra mass is helping hold those it's holding the stars in, so they can't be flung up. The gravity is exerting a greater force on the stars on the outer edge. So this is really well explained by dark matter, and that's one of the first good evidences. So we're going to open this and hope it shows up. Yeah. So on the left is the rotation of stars around the center of a galaxy if all there was visible matter. So this is what we expected. You can see that the stars on the outer edge are moving slower. This is why you got that rotation curve we expected that drops down. But what we actually see when we look out at almost all galaxies is this on the right, where the outer ones are moving really, really quickly. So you can kind of picture in your head, well, these guys should be ejected from the galaxy unless there's something else there that's holding them in place. And that's something else is dark matter. So that can't be the only evidence, right? Let's talk about some of the other evidence. The next piece of astronomical data we use to study dark matter is something called gravitational lensing. So this is an outcome of Einstein's theory of general relativity, and I won't get into the nitty-gritty, but the basic idea is that matter can bend space and time, and this bent space and time can deflect the trajectory of light passing through it. So if I had a really strong black hole in this room, and I was shining my laser pointer, instead of my laser pointer going in a straight line and hitting the wall, you'd actually see the laser pointer dot appear over there, because the photons would be bending through space-time. And so the neat thing about this is you can use gravitational lensing as a scale. If you can see how much light from a distant galaxy is being deflected, then you can calculate how much matter is in between doing the bending. And so this is great. There's a little cartoon of it here. We've got the light from a distant galaxy coming and being bent, and then reaching us on Earth when it's directly behind the sun and we shouldn't be seeing it. So you use this gravitational lensing as a scale, and you measure how much matter you think is in this pocket, and then you compare it with the visible matter. And if the rotation curves were just some fluke, your visible matter should equal the matter used in gravitational lensing. But you don't. You get the exact same answer, again, that there's 5 times as much dark matter as there is visible matter. So we always see dark matter hanging out with regular matter. And so this picture is a really, really famous picture called the bullet cluster image. And so what you see here is 2 galaxies. And this little guy on the right is just shot through the bigger one on the left. And so the blue and the red is the visible matter. This is like the stars and the dust and the gas that is heated up during this interaction. And the green blobs are where most of the matter is when you use gravitational lensing. So what's happened is this cluster, used to be sitting there with its dark matter halo, and this cluster used to be sitting there with its dark matter halo. But when these 2 things blew through each other, the normal matter interacted, hit each other, slowed down in the middle, and then the dark matter halos just passed right through each other and kept going. So you can actually see a separation of the dark matter and the visible matter. And this is another really, really unique clue that there is something out there. It's not just some fluid. So there's a whole bunch of other evidences. One of them Ross touched on briefly in an earlier talk was the cosmic microwave pattern. So if you could look out in the skies with, look out at the universe with microwave eyes, you would see all of these hot and cold spots. And these are leftover microwaves from the Big Bang. So after the universe cooled and expanded to a certain age, all of these photons were free, and now we're seeing them here on Earth. And you can actually explain these spots really, really well with a really simple model that only has 6 parameters. And the great thing about this simple model is it gives you out 2 important parameters: the total mass of the universe and the total baryon or normal matter. So if those other 2 things were flukes, this should give you the same number. But it doesn't. It gives you the exact same number you were getting from galactic rotation curves and gravitational lensing studies. There's 5 times as much dark matter as normal matter. So the other thing you can do is you can look out really far away at really distant galaxies and see, on average, how does space look? Like, are galaxies kind of neatly ordered and evenly spaced? The answer is no. They form this web-like kind of filament structure. So if you look at where all of the galaxies sit in the universe, they kind of tend to clump together in these groups. And if you want to reproduce this, you do a little simulation of the Big Bang. And you can't reproduce this large-scale structure where galaxies sit without accounting for dark matter. So there's a ton, there's 80 years worth of astrophysical evidence all pointing towards dark matter. So hopefully I've convinced you that we think something's there, and if we think something's there, we should talk about what it is. So the first idea for what dark matter could be was something cleverly named MACHOs, and that stands for massive compact halo objects. So these are things like black holes, neutron stars, and brown dwarfs. These are things that are regular matter or were once regular matter, really small and dense, and don't give off much visible light. And so maybe that's why we hadn't detected them earlier. So neutron stars and black holes, like I said, are really dense. They're as if you took the sun and all of its matter and you compressed it down into a little tiny sphere the size of the Earth. So they're really, really dense. Brown dwarfs are just stars that failed at life, and they didn't have enough gas, so they didn't actually start producing lots of fusion and giving off light. So again, they're hidden around, but they're really, really hard to see unless they're really close to us. So they did studies. This is one of the first things they looked for, and they put telescopes in space. And basically, if you look at a distant star and you wait, and a black hole or a neutron star passes between you and the star blinks at you. So you can do these micro-lensing studies using what you know about general relativity to look for MACHOs, and they found that there were, a decent amount of these, but they could only probably account for 10% of the total dark matter budget. There's no way they could account for all of the dark matter. So this is a form of dark matter, but it is ruled out as, the primary form of dark matter. So they can get into all these crazy things because theoretical physicists need jobs too. And so you propose all of these candidates and you say, well, maybe it could be this, let's test it. Neutrinos are a really, really good candidate because they kind of fit the bill. They have mass and they interact weakly, but not with electromagnetism or the strong force. And so people thought, oh, well, it's probably just neutrinos, right? We can detect these from the sun. We've detected them from stars exploding. But they were ruled out by early dark matter experiments. So So if it is a neutrino, then it's not the type of neutrino we're used to seeing because they just weren't there in the early dark matter experiments. There's another type of particle called an axion. So this is something that's extremely tiny. Like the electron is many orders of magnitude smaller than the proton and neutron, which are many orders of magnitude smaller than us. And axions are, tens of orders of magnitude smaller than that. So people have designed really clever experiments to look for axions, and they haven't turned up yet, but that doesn't necessarily rule them out as a possible dark matter candidate. I'm going to mention it. It's modified Newtonian dynamics. So this is something physicists thought, when they first saw rotation curves, well, if you guys are using gravity, maybe you just don't understand gravity, right? Like, why are you, so cocky that you think you know gravity perfectly? Well, so you modify gravity. You say, maybe it's a little bit stronger at longer distances or something, and that's why it's holding these stars in place. The problem is, modified Newtonian dynamics can only explain rotation curves. It can't explain the large-scale galaxy structures. It can't explain the bullet clusters, any of the things with gravitational lensing. So it fails on all accounts. And even the people who still try to publish papers on modified Newtonian dynamics still admit it can't account for all of dark matter. But this is something we've thought about, and gravity has, really stood the test of time, and we think we understand it well. So we should put faith in gravity when we're, thinking about the information it's giving us about dark matter. So a favored dark matter candidate, and my personal favorite, is something called a WIMP, because who doesn't like to cheer for these WIMPs? So WIMP stands for weakly interacting massive particle. And it is truly the dark matter particle that this universe deserves, because it just explains all of the data so well. I'm going to say it's heavy, and so heavy means maybe it weighs about 100 proton masses. If you don't know what a proton weighs, well, it's about the size of a tin atom. Let's say that's how much it weighs. So it weighs as much as an atom we're used to seeing. It's slow moving, but I mean relative to the speed of light. So we think it moves probably about 300 kilometers a second. I mean, that's fast by car standards, but only 0.001% the speed of light or something. And the third thing is weakly interacting. That's right in the name. That means we know it interacts with gravity and has mass, and maybe it interacts using the weak force, and this would explain why we haven't detected them on Earth yet. So if it's so elusive, Rhys, how are we going to find them, right? Okay, well, there's three general methods. I'll go through them briefly here, and then we'll talk about each one in detail in later slides. So the first way is to create it on Earth. Not in the sense that Nibbler creates it in his litter box, but using particle accelerators. We'll talk about that. The second way is you can look for another type of evidence that's not based on gravity directly, but you're not exactly directing the dark matter. You're not detecting it directly. You're detecting it indirectly. So you're looking for a call sign, if you will. And then the third way, my favorite way, because that's what I work on, is looking for the ambient dark matter, so the stuff that was created in the Big Bang, and watch for it very, very rarely colliding with normal matter. So these are the three ways that physicists are trying to detect dark matter. So the first way, creating it in a collider. So physicists are hoping that at these really big, expensive machines they've built, you can actually make dark matter. And so I hope most people have heard of Einstein's E equals mc squared. And what this is saying is, if you take two atoms or two protons and you speed them up really quickly, you're giving them a whole bunch of energy, E. And when you stack them together, you can turn that energy into mass, because mass is on that side of the equation. And so hopefully you can create some dark matter in these collisions from E equals mc squared. And then basically your dark matter flies out of your particle detector, and you don't detect it because it's weakly interacting, right? So the Large Hadron Collider at CERN is trying to detect dark matter in these collisions and notice it as missing matter in a reaction. So I'll try and put in an analogy. It's similar to you going in to get groceries, and you come out and you notice this big dent in your car in the paint street, and you say, well, there had to have been another car here because my car wasn't dented when I went in to get groceries. So you notice it through its absence, but we understand the particle interactions really well, and we know you can back calculate how much matter something had when it flies off in this direction and some other particle you see fly off in that direction. So option number 2, indirect dark matter detection. So I was telling you guys that matter bends space and time. So you can think of this, if you have a really massive object like the sun or a black hole, it actually makes a little well, a gravitational well they call it. And so if there's a whole bunch of dark matter hanging out from the early universe, you can get more dark matter than average in this gravitational well. So on average you have more dark matter, and if they have a self-interaction, then there's a chance that the dark matter particles will collide with each other, and when they collide, they'll give off some other particles which we can detect. This is the hope. So the signal would be looking at the center of the galaxy, or looking at the sun for high energy neutrinos or cosmic rays, and then saying, hey, there's nothing in that sun that could have created this. So this is a telltale sign of dark matter. And so what you do is you build a neutrino telescope, they call, and you look for neutrinos coming from the sun. So there are actually researchers at the U of A working on this project called IceCube, and it's basically a whole bunch of light-detecting instruments buried in a glacier on the South Pole, and it's 1 cubic kilometer. So when a neutrino goes through the ice and it creates a particle, the particle rips through the detector, and it makes this little cone of light, which you then see, and then you add up all of the light, and you can actually point back and say, okay, was that a high-energy neutrino coming from the sun or the center of the galaxy? And that would be a way to indirectly see dark matter, but there has been no conclusive proof yet. There have been really interesting hints from a lot of these experiments, but there's been nothing conclusive claiming to have found dark matter. And the third and best way, because it's what I worked on, is to directly detect dark matter. So you're probably thinking, well, if it's so easy, you just build a detector and look for it. Why haven't you guys done it already? Get on it. But the problem is, particles come from the sun all the time. Well, particles come from radioactive decays. So even though we can't see it with our eyes, if you built a really sensitive dark matter detector and placed it here in CSIS, it would just glow the whole time from background. It would glow from things coming from space. It would glow from radioactive decays coming from walls. There's too much background on the surface of the Earth to be able to see a faint signal, a rare interaction like dark matter. So what you do is you dig a really deep hole, and all of the overburden, all of the rock blocks out the cosmic rays, and then you build the cleanest detector you can to get rid of all of the radioactive backgrounds. And if you have a really clean detector and it's really deep and there's as few backgrounds as possible, then you have a hope of seeing it glow once in a while from dark matter hitting it. And then you have to look at the light that comes off and say, okay, that was definitely dark matter and it wasn't just something boring like an electron or an alpha particle. So this is my little schematic. Dark matter, which is represented by a eye, pops in here and it kicks out some light and you pick up the light, or it kicks out electrons and you can detect the electrons, and then it goes on its merry way. The world-leading experiment for this is in Italy, in a laboratory called Gran Sasso. So the Italian government actually drilled a tunnel through a mountain, and then some physicists said, hey, can you guys build us a little laboratory in the middle of this mountain? So they actually have like a deep underground lair, if you will, within their dark matter detector with a lot of backgrounds. And they have the world-leading result. They put a bunch of really clean xenon in this cylinder, and then they wait for dark matter to hit it, and they haven't seen anything yet. And the experiment that I'm working on is a mostly Canadian experiment, so you guys can be proud, and it's being built right now in Canada, near Sudbury, Ontario. So we have a nickel mine that's over 2 kilometers deep, but we asked them to blast out this cavern for us, and then we coated the walls and cleaned everything up as best as we could. And we're building this 2-meter wide sphere of acrylic, which is the material they use when they make the glass planes at hockey games. So we have this 2-meter sphere, and we're going to fill it with a really pure chemical, and then wait. And if dark matter exists at the level we think it does, or it has the interactions and the mass we think it does, we should see this thing light up every now and then when dark matter smacks into it. And then a few Canadians maybe can get the Nobel Prize. So to summarize, let's just go back over it quickly. Dark matter makes up 27% of our universe. We've only really detected it so far because of its effects on visible matter, and that breaks down to gravitational influences. So physicists are really racing to detect it on, anywhere you go, Japan or Europe or Canada or the States, every other country which has a good particle astrophysics budget is looking for dark matter in some way. And then we went up with three methods: indirect detection, direct detection, and creation. But the mystery remains. It's still waiting to be solved, and it's a fairly old problem. So I'll leave you with a quote by one of physics greatest, Albert Einstein. He said, "The most beautiful experience we can have is mysterious." So, thank you very much.
So in the Italian experiment or the Canadian one, once you get that going, 2 meter wide, how often, based on your current understanding, would you expect there to be a dark matter interaction?
So this is something you have to tell the funding agencies, right? How long until you get a return on your So if it has the cross section we think it is, and that's sort of fancy word of saying when dark matter is going through space, how big does an atom look to it, right? If it has the cross section we would like, and the mass we would like, we should see 2 or 3 interactions in about 3 years. And our detector is so clean, based on everything we know, we've accounted for every variable we could think of. We should have something like 0.5 background events that look like dark matter. So we need to see 3 or 4 events, just a handful. But we know our detector should only ever have maybe 1 background event at the most in 3 years from it. That looks like dark matter. Anyone else question?
What about the velocity, I guess, like dark flow? So how does that work in realm of dark matter?
So dark flow is this mysterious thing where if you look out, galaxies and clusters of galaxies should be moving about in more or less random directions, right? But they tallied up a bunch, and it seems to be that there are a couple superclusters moving in some general direction in dark flow. But that's on a really, really grand scale, and so it doesn't affect what we think about the velocity all that much. So when I said the velocity was 300 meters a second, I was telling you the average. So we think the velocity has some distribution. So let's say that 90% of the dark matter will have velocities between 300 kilometers a second plus 50 or minus 50. So between 250 and 350. There's this distribution, and dark flow doesn't add into it all that much, but you could account for it if you really wanted to.
I think there's a question at the back.
Yeah, okay, one point at the back.
Assuming that most of the dark matter is in the galactic core, and it drops off as you get up towards the edge. By the time you get to where we are, how come it doesn't affect the planetary motions enough for us to have detection?
That's such a great question. Okay, so I'm telling you there's a lot of dark matter, but that's because we're looking really far. So if you were to do a calculation, take all the dark matter we have in the universe, and then divide it by the amount of volume we have in, say, the Milky Way, there would be a dark matter particle in every fist-sized area. So there are actually tens of thousands of them passing through all the time because we're moving through. But that's still not enough. On the scale of the galaxy, or say on the scale of the solar system, there's just not enough dark matter to actually influence the motion of the stars. So this is why it took so long to detect it, because there's a lot of it, but it's really, really spread out really thinly. So we don't notice it until we go to the scales of galaxies. But on the scale of the solar system, there's just not enough there. Think about, there's 6 times 10 to the 23 atoms in every mole of some material, and there's 1 dark matter particle in every fist-size area. So my fist has 6 times 10 to the 25 times as many atoms, roughly. That's my back of the envelope. So there's just not enough of it here. Sorry, I got excited. Do we have time? Anyone else? This way you can maybe have.
Oh yeah, I was just wondering, you said there's different places on the Earth that are looking for dark matter, but what about like on a space station or something like that?
So this is a good question too, because when you build a telescope, it's better to place it in orbit sometimes because there's less interference from the atmosphere. But for a dark matter experiment, it's suicide to put it in space because you're getting cosmic rays coming from the sun too, right, and hitting the atmosphere. So if you put a dark matter experiment in space, you're actually exposing it to more cosmic rays. You want as much shielding around it as possible. And the cheapest way we can think of doing it, instead of building 400-meter lead walls, we use mines that people have already done, and we go really, really deep. So they do have indirect dark matter detectors in space. There's one called the alpha magnetic spectrometer, but it's an indirect one. It's looking for antimatter that would come about because of dark matter collision. So they do have dark matter experiments in space, but they're not direct detection.
Okay.
One more.
Is there a reason why dark matter stays so diffuse, or could it clump up and form like masses or?
So the main reason it stays diffuse is because it's so weakly interacting. So you would think if it could interact more often electromagnetically, that it could bump into each other and then slow its velocity, and then when you slow it down, you kind of get like a bundle of it, and it slows down more and more and more. But because it's so diffuse, most of the time it just passes right by normal matter and itself. And so, like I was saying, the only way you can get a higher than average concentration is when you have a gravitational well, because we know it has mass and interacts gravitationally. So you need something really heavy like a black hole or a sun, and then when dark matter is going by that, it kind of gets deflected and maybe gets stuck. And then all of a sudden you have a whole bunch, but they're just so weakly interacting that they can't, it lets them stay really diffuse and spread out because they just don't interact with each other or normal matter very often.
Thank you very much.